It is my pleasure to introduce our next speaker, Tushar Das. The title of his talk is Dimensions of Continued Fraction Cantor Sets. Please go ahead.
Thanks, Mrinal. Thanks to all of you for staying on a Saturday to hear about continued fractions. Several speakers spoke about them in their talks, so that was fun to see. So it's the last talk of the session. It's really nice to see that there's people from all over the world here. And it's kind of getting close to lunch in Wisconsin where I am. So I'm dreaming of all this good food that all of you are hopefully going to eat later. Okay, so all the work I'll talk about is joint work with my brilliant collaborators who are also friends and teachers for me. And pretty much I was thinking about this the other day that my entire mathematical career has seemed to be a footnote to what Felix Hausdorff did. And so he was a big mathematical hero of mine since I was an undergraduate. My slides will be shared with you by Mrinal. There are links to anything in this color is a link. And so many of you may not know that Felix Hausdorff had a double identity, and he was also Paul Mongret, and he wrote several works on philosophy, literature, art under that name. And so we'll be studying a very key idea that he introduced known as Hausdorff dimension, which allows us to study intricate fractal sets that are invisible to Lebesgue measure. So where are these fractals coming from? Let's start with sort of the simplest example. And you heard in Andre's talk at the start of the session about conformal iterated function systems. That's a CIFS. And this is a favorite CIFS of mine. It's the Gauss map. So it's the map X maps to 1 over X mod 1. So here are the details. We want to look at inverse branches of that 1 over X mod 1 map. And these inverse branches are of this form. So for each positive integer I, you look at the Mobius map, X maps to 1 over I plus X. And we're going to look at collections of these maps. So for any subset of positive integers E, you could call that an alphabet. The collection of maps GI, where I ranges over E, is called a Gauss CIFS, a Gauss conformal iterated function system. And if you take the alphabet to be the entire set of positive integers, then you get what's called the Gauss CIFS. And those of you who are familiar with continued fractions know that this is very much related to representing real numbers by the continued fraction format. So here's the link. If you take these GI maps and you iterate them, you notice that you get continued division occurring. And so in particular, if I look at the orbit of 0 under a word omega, then I'm going to get this continued fraction representation, which is shorthand for this object up here. Okay, so this technically it means you have 0 integer part, and then here's your fractional part. It's 1 over some positive integer plus 1 over another positive integer all the way down. Okay, so we're interested in limit sets of Gauss CIFSs, and these are typically fractal sets in the unit interval, and they're formed just as you would form any fractal set by an iterative procedure. So you just define it as this sort of a intersection of unions of images of 0, 1. So this is the same format as you probably were introduced to the middle third Cantor set when you were an undergraduate. Now, given an alphabet E, I can think of this number theoretically as just nothing else. This limit set Fe is just the set of irrationals whose continued fraction digits, and by the continued fraction digits, I mean these omega 0, omega 1, and so on, all of whose continued fraction digits lie in this set E. Okay, so the study of such sets started soon after Hausdorff introduced his notion of Hausdorff dimension. One of the pioneers was Wojtek Jarnik, and another pioneer was Abraham Besikovich. And I'll tell you a bit about both of them and what they did. So Jarnik considered the set of all irrational numbers whose continued fraction digits are all up to a certain bound. Okay, so let's say that parameter is n, and so you only allow continued fractions whose digits are between 1 and n. I'm going to call that f less than equal to n for obvious reasons. And in 1928, Jarnik was able to prove that for n greater than equal to 8, you have the following bounds on the Hausdorff dimension of this fractal set. And his methods were very arithmetic. He used a lot about the arithmetic theory of continued fractions to get this bound. And that was in 1928. And that was the kind of state of the art until he had his student, Kurzweil, who he gave the following problem as a thesis problem. So Kurzweil's thesis, you might have heard of Kurzweil because of the Kurzweil-Henstock integral. He actually is an incredibly prolific mathematician with, his work has several applications to various areas of mathematics. But anyway, Jarnik gave this excellent student, Kurzweil, then in 1949, the object of trying to improve his bounds. And so Kurzweil could improve them, and he could prove the following improvement. So you'll notice that the log terms have now disappeared, and he could prove that this dimension is between these two bounds right here. I'll just mention, for those of you who are interested in higher dimensional generalizations, these f less than equal to n's are related to what are called badly approximable numbers. And the badly approximable numbers are the union of these f less than equal to n's, and they're a full Hausdorff dimension, even though they have Lebesgue measure 0. So they're a large set of numbers, and you might be interested in approximating larger systems of linear forms rather than just single real numbers. And so there's a matrix approximation framework, and Kurzweil's bound right here has been generalized by my brilliant collaborator, David Simmons. And so you can see his paper by clicking on this link if you're so interested. Okay, but let's come back to one dimension. The next result after 1951 was in 1992, so several decades later, when Doug Hensley wrote a beautiful paper that gave the following asymptotic for the Hausdorff dimension of f less than equal to n. Now, as a personal note, this formula was given to me, this paper was given to me by my undergrad supervisor, the late Bernd Stratmann. And I remember this was a very favorite formula of Bernds, and he gave this to me. And he didn't tell me anything about it. He just wanted to see what I would feel. And I was very haunted by this formula. And so we worked on it, on and off since I was an undergraduate. And we only managed to really, there's so many questions when you look at such a formula, right? You could say, well, can you guess what these coefficients are? Can you guess what the next term is? There's several questions, and so I couldn't make any progress on it until several decades later. Okay, so let's change gears slightly. Instead of f less than equal to n, let's look at a slightly different setting. Okay, so we're going to go back, we're going to rewind back to the late 1930s and early 1940s to Jack Good, who was actually Isidor Jacobus Gudak, but he changed his name to Irving Jack Good, probably to avoid you know, ethnic aggression against his background. And at the time, he was a grad student, and these were his advisors, Besikovich, who I mentioned earlier, and Hardy. And he said at the time, I think what I liked most was the amazing formulas, such as those of Ramanujan. And Besikovich gave him the following problem, just like Yarnik gave Kurzweil. He said, well, why don't you study sets of Hausdorff dimensions of sets of continued fractions? And I just want to point out that Good's results, which I will show you on the next page, won the Smith Prize in 1940. So that's the top prize at Cambridge. A few years before him, Alan Turing had won that prize. And basically every top student at Cambridge was then picked up immediately after winning this prize and moved out of university into the war effort, right? So both Turing and Good worked at Bletchley to help with code breaking. So he says here, I found, for example, that the set for which the partial quotients, these are the continued fraction digits, an, they tend to infinity. That has a Hausdorff dimension of a half. And you'll notice he calls this a fractional dimensional number or a fractal number. It wasn't called the Hausdorff dimension back then. So here's one of the big results in Good's thesis, which is he looked at f greater than equal to n. Okay, so as opposed to allowing your continued fraction digits to be 1 through n, you now let them be n and larger. So he proved in 1941 that for n greater than equal to 20, you have the following bounds. Okay, and there was several progress, but I'm going to just skip a lot of years now. There was progress trying to improve Good's results by Cusick, Ramharter, and then most recently by Urish Kesselbaumer in 2010. So what we could do is we could kind of complete find full asymptotic expansions for both the Hausdorff dimension of f less than equal to n and f greater than equal to n. So here's the full asymptotic expansion for f less than equal to n. This was, this was the final result in this vein was Hensley's formula. And you might wonder whether Hensley's coefficients show up, and it is true they do. They form a kind of a subdiagonal sequence here. So the Ci, comma I minus 1 sequence is given by this formula right here, and you can see the reciprocal of zeta of 2 showing up. And what's interesting is all the other coefficients are, we haven't done this, but if you're interested in numerics, everything is numerically computable to arbitrary precision. But there's no simple closed formulas that we could find for the otherCijs. In the case of f greater than equal to n, you get a much more intricate asymptotic expansion, as you can see here. Yeah, when we first came up with this, we were very, very surprised by it. And we were kind of asking around, has anyone seen any expansions like this in in any area of math that they'd been studying. Yeah, if I extend that same query to you, if you've seen, if these expansions remind you of something, it doesn't have to do with Hausdorff dimension even, please let me know. I'll be very curious. Okay, now in this case, the coefficients again are computable, but what's very interesting now is that we can prove that all the coefficients, so these CKLs, the CIJKLs, they are all rational numbers in this case. Okay, so what is at the heart of both these results? It's basically a piece of, I would say, elementary functional analysis, which is a perturbation theorem. So here's the setup for what's at the core, what allows us to prove such results. We're going to let B be a Banach space. Elements of B vectors will be F. B star is the continuous dual, and elements will be denoted by sigma. And L of B will be the Banach space of all bounded linear operators from B to B. Okay. If it helps, if you're not so familiar with this language, if it helps, you could just think of L of B being square matrices and elements of B being column vectors and elements of B star, the dual, being row vectors. So you beyond that, you won't need anything else to understand the result that I will present on the next slide. And so then here's some notation. If I take an element of the dual and I apply it to a vector, then I, of course, get a scalar. And so sigma f would be a complex number, whereas f sigma would be a linear operator, and sigma L would be an element of the dual. Okay. I'll also be needing the idea of fixed points. So f is going to be called a right fixed point of L if L of f equals f. And similarly, sigma will be called a left fixed point of L if sigma L equals sigma. Okay, so this is basically saying you're either a fixed point of the operator or you're a fixed point of its dual. All right, so here's the theorem. So suppose we have two operators, L and L prime. In our applications, you should think of L prime as being a small perturbation of L. And so say you have two operators, L and L prime, that are bounded linear operators, and they have right fixed points. Okay, so L of G equals G, L prime of G prime equals G prime. And let's assume also that L has a left fixed point mu. So mu L equals mu. And then we have this normalization. We assume that mu G or mu G prime aren't zero. So then we're going to define a new operator, R, which is going to be L minus CG mu, where this constant C is 1 over mu G. And we have to assume that this operator, we can form a Neumann series for it. So we're going to assume that its spectral radius is strictly less than 1. So let's now form the Neumann series. So the Neumann series for R is Q, and because the spectral radius is less than 1, Q now defines a bounded linear operator, and we can finally define the quantity that's very key in this whole story, which is the perturbation. So delta is the difference between L prime and L. So the result then says that if we have a condition that now allows us to form the Neumann series for delta, then we get this scalar equation. Okay, so it looks like a complicated equation, but it's actually solving this equation is at the heart of the formulas I showed you in the previous slides. Okay, so yeah, this is the punchline. for the theorem. I just want to just emphasize that this is a scalar equation because you've got a bunch of operators acting on a vector. So this 0 is just a scalar. Okay. So how do we use this theorem, which I called a perturbation lemma, to prove those results about the Hausdorff dimensions of f less than equal to n and f greater than equal to n? So this now takes us to what's called the thermodynamic formalism, which was a group of methods that were inspired from statistical physics and imported into mathematics and dynamical systems in particular by Bowen, Ruel, and Sinai. And so that Gauss map, which we started with, has a associated transfer operator, which we call L. And here's the form of this transfer operator. This is what it does. And we could look at two different ways of truncating this operator. One I'm going to call L less than equal to n. So this one is a finite sum from 1 to n, and then you've got L greater than equal to n, and this is an infinite sum. You'll notice that the other main difference here is this exponent 2, the exponent 2 times delta less than equal to n, and 2 times delta greater than equal to n. So in some sense, you should think of this exponent as being the derivative raised to the power of 2s. And s is a parameter which is 1 here, which is the Hausdorff dimension of the entire interval. S here is delta less than equal to n, which is the Hausdorff dimension of the set of all points, f less than equal to n. So the set of all points whose continued fraction digits are at most n. And similarly, delta greater than equal to n is now the case where s is equal to the Hausdorff dimension of f greater than equal to n. Okay, so this, I call it a celebrity operator because it's been studied for over 100 years, is often known before the thermodynamic formalism as the Gauss-Kuzmin-Versing operator. It was studied long before the thermodynamic formalism was a thing in mathematics. So this operator fixes this positive function, g of x equals 1 over 1 plus x. This is a renormalized density, invariant density, and the dual of this operator L star fixes Lebesgue measure. Okay, so this is an absolutely continuous density. Now, how does this relate to Hausdorff dimensions? How do we relate this to calculating the Hausdorff dimensions? Well, it's all encoded because of these exponents, okay? So the fact that, by the way, this notation, I hope it's not confusing, the box, the empty box basically means you can put a less than equal to or a greater than equal to sign inside the box. Okay, so I'll just say it with less than equal to n. So delta of less than equal to n equaling the Hausdorff dimension of f less than equal to n is equivalent to saying that the spectral radius of this L less than equal to n operator is equal to 1. And the fact that this is a positive operator, its spectral radius equals 1, is also equivalent to saying that L less than equal to n has a right fixed point and that its dual has a fixed point as well. So it has a right and left fixed point. So that's what the connection is between functional analysis on the one hand and Hausdorff dimension on the other. Okay, so now that you have our theorem and you've seen how the thermodynamic formalism relates Hausdorff dimension to operator theoretic information. So what you do is to get the expansion for f of less than equal to n, you apply our perturbation theorem with L being the Gauss-Kuzmin-Versing transfer operator, and you let L prime be L less than equal to n. And then the punchline, the conditions are all satisfied, and then the punchline of our theorem tells you you've got this implicit equation. Okay, so this is a equation, And I'll just remind you that this delta less than equal to n is hiding inside it, right? Because delta less than equal to n is inside L prime, and L prime is very much part of this equation. Okay, so then the idea is you've got this complicated equation and you have to solve for a variable, and so you use the implicit function theorem. And when you do that, you get this asymptotic expansion. Okay, so that's the heart of this first proof. And then there's a similar strategy for the other proof. Okay, so I'm going to skip that and I'm going to move on to what else we can do. So you heard in one of the previous talks about the Virahanka sequence, also known as the Fibonacci sequence. So you could ask yourself, okay, what if I allow my alphabet to be this sequence 1, 2, 3, 5, 8, 13, 21, etc., and let delta denote the Hausdorff dimension of that set. Okay, so all irrationals whose digits are Fibonacci or Virahanka, and let delta less than equal to n now be the Hausdorff dimension of irrationals whose digits are within the first n. And similarly, delta greater than equal to n, the Hausdorff dimension of the irrationals whose continued fraction digits are the nth Virahanka number and greater. Okay, so the nth, the n plus first, and so on. So in the less than equal to n case, we get this beautiful formula. And I want you to notice that this is not an asymptotic expansion. There's no big O term here at the end. So this is a convergent series for n large. And it is not surprising, I'm sure, to experts here that you get both the golden mean and its conjugate appearing in this formula. Okay. And if you're interested in reading about this, if this was known to you, you could ignore this. But if you're interested in reading about, how did these Fibonacci numbers show up, and in one of our talks by Professor Tomar, we heard some of these names earlier. She mentioned Pingala and Virahanka and Gopala and Hemachandra. And there's a great article in Historia Math by Paramanand Singh that is linked to on this slide if you're so interested. Okay, now there's a analogous convergent series formula for delta greater than equal to n. As expected, it's a little more sophisticated than the less than equal to n case. But now there's a interesting thing I can say about these coefficients. Again, everything is can be numerically computed to as much precision as you want. But what is interesting now is that in the greater than equal to n case, when we were in the Jack Good world, these were all rational numbers. These are now in this ring. And this ring is interesting because you can, specifically say what are the elements that are showing up here. Okay, but in the less than equal to n case, all we can say is that they're arbitrary real numbers. We don't have any other information about these coefficients. Okay, so I'm close to my end of my talk, and so I'll tell you a couple of things which we can't do. So here are the two simplest examples where our technology does not apply. So one is a very interesting Gauss CIFS. You allow the alphabet to be the prime numbers, okay? And if you're interested, we have a paper about this recently, not about the Hausdorff dimension as studied here, because we can't solve that problem, but there's another dimension theoretic problem that we attack. You can look at that paper by clicking on this link. But our method cannot tell you an expansion for the Hausdorff dimension of the set of all numbers whose continued fraction digits are the first n prime numbers or the nth prime number and beyond. In both those cases, we can't solve this problem. So please try your hand at it. Here's a simpler example that we can't do. This is a similarity IFS. So unlike the other ones, which were these nonlinear uh, rational maps, the similarity IFS is an example where all the maps are similarity maps, so constant derivative. And we call it the co-Cantor set. So this set is the IFS is basically you take the Cantor set, and then at every level, you have an interval, which is a gap, right? So at the first level, there's one gap. At the next level, there's two more, and then so on, right? And so um, this IFS, the generators takes all those gaps and you map them via similarity and affine map onto the whole interval 0, 1. So there's your infinitely many generators. We can't figure out how to get asymptotic expansions for that. So I'm running out of time, but there are several other examples to talk about here. And maybe I'll just end with there's a project that I'm working with my friends here, Anna Zunik, Giulio Tiozzo, and Mario Shurbansky. And we took this example of the Hausdorff dimension of f of less than equal to n, and we tried to generalize it to the setting of open dynamical systems. And so this f less than equal to n set is what's called a survivor set of points that don't fall into a hole under forward iteration of the Gauss map. And this is a story that's ongoing. Volume 1 will be published about in a month. So I hope to report on that at a future iteration. Sorry for going over time.
Thanks to the speaker. Any question?
I had a question.
Yeah, please.
Yeah, thank you for the very interesting talk. I missed the part about the connection to the thermodynamic formalism,
Yeah.
but if you don't mind repeating the connection, do you
Yeah,
connect
yeah.
the Hausdorff dimension to entropy or pressure?
Yes. Uh, Entropy doesn't show up here as much, but pressure is hiding inside all of this. I've just chosen not to emphasize pressure, but yeah, pressure is very much here because
Right.
if you take e to the power of the pressure, you're going to
Mhm.
get the spectral radius of the operator. So that's the connection with pressure.
Right.
Uh,
And in that case, in that pressure calculation, what is the potential that you choose? The
oh, right.
phi. Yeah,
Yeah.
yeah.
So what's phi?
Hmm.
Um, Phi is so you can sort of see it in here. Can you? It's what we call a geometric potential. So it's minus log of the derivative raised to the s. And I didn't add that formalism for this talk, but it's hiding here. It's this term.
Understood. Right.
You see these weights? You can think of them
Yeah,
as
yeah. I told you.
those are the potentials. And it's
Mhm.
often called a geometric potential. If
Geometry.
you look at any of the books of Mario Shurbansky, for example, or Yasha
Mhm.
Pessin on dimension theory of dynamical systems, this is often called a geometric potential because it
Geometry.
allows you to get a handle on the Hausdorff dimension of the limit set.
Right.
Um,
Right. So
if
this
you,
makes the connection. So this choice of the geometric potential is the bridge between the Hausdorff dimension
exactly, you see,
and the
that's
potential differential.
why these numbers show up in the exponent. Do you see? These are the
Hmm.
Hausdorff dimensions.
Right.
Exactly.
Right.
And so, yeah, eh, we don't have time to go into it here.
Yeah.
Please ask me more questions.
Of
But
course.
if you look at my slides, you'll see a you'll see much more about how the thermodynamic formalism as related to conformal IFS, right, like the Gauss
Right.
map, can be generalized. And you could look at it in terms of Kleinian groups, or you could look at it in terms of um, holomorphic, rational, or meromorphic dynamics. Yeah.
I see.
So
It's
there's
very
a lot
fascinating.
of work to be done here. I think that if you don't like continued fractions, but you like dynamical systems that are like, that give you Julia sets or that give you Kleinian group limit sets, there's a lot of work to be done to get similar expansions in these settings. There's some initial work that's being done here. By these authors right here, but there's a lot more to be done. Yeah. Did you have another question? I'm sorry.
No, no, that was very interesting. Thank you very much.
You're welcome.
Is there any more question to the speaker? If not, let us thank the speaker again. So our next talk will start almost after 2 hours. See you then. Bye, everybody.
Thank you.